Hello, so I just wanted to summarise some preliminary results I got from my inversion of SMRT. To evaluate the inversion, I needed to pick some test data, and I chose a 3-day long section of continuous backscatter measurements taken by the KUKA from the 29th of November to the 2nd of December. And I resampled those profiles at a 3-hourly frequency. And I could potentially increase that frequency, but this is just sort of a first rough and ready run. It's a 2-phase process, so the first thing is to take the first backscatter signature that you see in the time series and perform a really big global search to match the geophysical parameters to the observations, the backscatter observations. And then using the best fit that you can find for the t=0 first backscatter signature, you then iterate the inverse model using a simpler routine to try and estimate the evolution of the geophysical parameters. So here's the first time step of the test data that you can see, and that's where you have to put in a lot of time to find the best to run the inverse model in a way that gives you the best input parameters for the observations, and then once you've done that, you can evolve it more simply and try and match this evolving backscatter profile. And the first thing to notice is that not a lot happens here. So I wanted to find the simplest case where not a lot changes, and that's fine. So the global search had these results visualized as a histogram. So most of the minima that I found were in the range of sort of 6 to 8, but I could do better. And the lowest minimum that I found, and the one that I went with to feed the tracking algorithm, was 3.98. So it's pretty easy to do okay, to get a fairly good fit, but it's hard to get a really good fit. This is one way of visualizing all of those minima. I've just taken 5 variables, but there were 12 being fitted. But the 12 by 12 graph is not very legible or understandable. I've ringed the lowest minimum in red, so you can see how that exists. But also theoretically, each of these graphs should show a surface, and we're looking for the minimum of that surface in all of the different dimensions. Or at least for all of the different pairs of dimensions. And there's no easy wins here. There's no I was sort of hoping that some of the surfaces, there would just clearly be a region of minima where we could tighten the bounds, but that doesn't seem to be the case. Part of the problem is that the bounds mean that we sort of butt up against. As soon as you go out of bounds, the cost becomes really high, which leads to a minimum right next to the bound. So I need to think a bit about how I can improve the algorithm to stop all these minima occurring along the bounds, because they don't actually represent minima in the real surface. They just are an artifact of the bounding. This is how the best fit looks when you actually plot it against the observations. It's pretty good. So you can see at the top of the figure how all the values correspond to the bounds, and pleasingly they're generally in the middle of the bounds. They're not stuffed up against, so that indicates that they're not artifacts of the bounds. They're actually they correspond to a real minimum in the surface, and therefore a real best fit of the geophysical parameters to the observations. So with this, I use this as the starting point for the local search phase. So I take a guess, and I make some assumptions that the minimum corresponds in the cost function corresponds to the same basin, and then I just evolve the algorithm to track this evolving backscatter profile, which you can see does not evolve very much. So the main evolution is in the nadir looking range, where the Ka becomes significantly larger than the Ku for the copole. So They're about the same, about the same, about the same, and then suddenly the red line is going to emerge above the blue line. So that's really the evolution that I wanted to track. When does that actually happen? It's essentially 9 a.m. on the middle day. 9 a.m. on the 1st of December. So, a quick word about minimization algorithms. I did the global minimization with one local minimization component called SLSQP. I'm not going to go into the details of like what those letters even mean, because I found that was the fastest. But then when I wanted to do phase 2, it just didn't work for the tracking. Not exactly sure why, but I switched to another one which did work for the tracking. But that means that I found the global minimum with one routine and tracked the local minimum, the evolution of the local minimum with another routine. So that's something that can be fixed in the next model run. But it's important because there's a sudden jump in the cost function for the first time step, and I think that's just because I've mixed routines, and I think that's causing this jump in the cost function. But pleasingly, it seems like the cost function doesn't go up to where most of the minima were in that histogram that I showed. So this histogram shows that most of the minima are between 6 and 8, or maybe even 6 and 9, whereas the cost of this tracking stays below. It goes up to around 5 and then it comes back down again, and that implies that we're tracking the evolution of geophysical parameters that are a good fit, and they're not just a good fit, but they're an especially good fit. So that's quite good, and I'm hoping this initial jump will disappear. So here are the time series results from the local tracking mode. You can really see for the temperature and the snow depth and ice density and snow density and ice roughness that there is an initial jump. And again, I'm hoping that'll disappear when I use a consistent local minimization algorithm for the 2 phases. But the important thing is as well that the cost function doesn't go wild during this tracking phase, and also the geophysical parameters don't go wild, so they stay steady, and that's giving me a bit of hope that this model inversion is perhaps not doing the right thing, but it's doing something sensible, and we can coax it into doing the right thing. So how to move forward on this? The inverse model would be a lot faster if I remove some of these 12 variables. So I'm going to look into that, or at very least reduce the bounds on them. But it's not the case that if I halve the number of variables, I'd double the speed. If I halve the number of variables, I'd go faster by a power of 6 or something, by a factor of 2 to the 6. So that's quite tempting. The other next steps are, as I said before, running this local minimization routine in the global search mode. It will be a bit slower, but it'll be consistent between the 2 modes. Running the track mode on Myriad would be good, because it does take quite a long time. It takes half an hour or something for me to run it for this 3-day period that had only 24 time steps. So it'd be nice if I could outsource that to the electricity bill of UCL and not mine. Definitely pick a more interesting time series, because this was really just a proof of concept, but it would be nice to actually run it over a time series where we can properly track the temperature evolution, for instance, and see if we can back that out. And also I resampled the time series that I used for this analysis to 3 hours, but I think the evolution would be smoother and easier to track, and we'd have a better chance of assuming that we're staying in the same minimum if we did that at 1 hourly frequency.